I am working. My name is Taylor Leblond. I work with Fisheries and Oceans Canada with Harold Yerk. I am currently developing a PAMGuard module that takes data from the pre-existing whistle and moan detector module in PAMGuard and extracts features from it that are typically common in the field of music information retrieval. Hence the name of the project I have right here, Music Information Retrieval Random Forest Classifier. And I'm sort of developing it into multiple modules. Currently, I've mostly developed the feature extractor, which basically, for anyone familiar with PAMGuard, it has a module called the whistle and moan detector, and what it does is it processes the audio, turns it into a spectrogram, of course, and looks for contours that stick out in the audio, such as harmonics, which is what occur when whales make sounds. And it's pretty good. It's pretty accurate if you have the right settings. And most of the time, in fact, pretty much 100% of the time, except for this weird glitch it has where the first 2 seconds cause false detections, you can make it that every single detection is in fact caused by a contour and not some false thing. And the thing about that is that those contours can be anything. They can be killer whales, humpbacks, vessels. There's something, but the thing isn't, the module isn't able to differentiate between what is a killer whale, what is a humpback, what is a vessel, what is a California sea lion, etc. And this project, the primary goal of this project is to differentiate between killer whales, humpbacks, and anything that can set off the whistle and moan detector. So what happens is this data is sent into this feature extractor module I've made, which it saves audio clips whenever whistle and moan detections occur, and extracts features from it. And I will explain what those are in a second. With those features, they're saved into CSV files because they're easy to read. They can be labeled in a pre-existing plugin that I made a couple of years ago called the Whistle and Moan Navigation Tool, and can be managed into training sets in this training set builder module. And with those training sets, eventually these will become, I'm going to create modules for classifying. One of them will be for effectively testing the training set and seeing how effective it is. And the other one is for classifying live audio that is being run through PAMGuard. So feature extraction, effectively what happens is I'm able to save the audio clips briefly whenever a whistle and moan detection occurs. I mostly took code from the PAMGuard's clip generator module. PAMGuard is open source for anybody who doesn't know. And so these clips are saved, and I run them through some Python code. And I'm able to extract features from these. And some of these is just header data produced from PAMGuard itself, like amplitude, frequency, etc. But most of the calculations are performed by a Python library called Librosa. I think somebody else mentioned Librosa once previously. And these features are things like null frequency cepstral coefficients, spectral centroid. I'm not going to get into too much detail, otherwise we will be here all day. And there's a pitch tracker called Yin. You can use that for calculating certain things. And there's also some simple calculations. I created a feature, created. It's more like I came up with a feature and sort of gave it a name, and it probably already exists, where it just takes like the whole magnitude of the spectrum, like the average mean. And that's just a pretty simple calculation in general Python code. And the primary goal of this, as I said, was to be able to differentiate between killer whales and anything else that causes contours effectively. But a secondary goal of this project is to allow people to use the whistle and moan detector to classify anything that, anything that the whistle and moan detector can pick up. So if there's any other marine mammals, for example, that people want to classify, I have it set up so that people can customize the feature vector. They can pick whatever features they want to use, and they can test which ones work better, and then use those features in their classification. So the secondary goal here is it's not just for killer whales, it's also pretty much anything, and the intention is for other potential marine mammals. All the tests, the only tests we've done so far have been on killer whales, humpbacks, vessels, and a little bit of Pacific white-sided dolphin, but we don't have enough data for the last one. But I think I'm repeating myself at this point. But anyways, machine learning classification is performed with the scikit-learn Python library. And when tested on the current data set, the top 3 most accurate classifiers from the library were the random forest classifier, the extra tree classifier, which is a variant of the random forest classifier that uses different decision trees, and the histogram gradient boosting classifier. That last one I only recently started using. I can't really go into detail about how it works because it works quite differently from the other two. It works quite well, but I can't really explain it right now. I can explain the random forest classifier though, and I will do that in a second. So all 3 of these are examples of ensemble learning, which means that multiple learning algorithms producing their own outputs are used to produce a final classification, as opposed to one algorithm producing a single output. This is particularly useful to this task as it allows us to prioritize detections where the classifier has a higher certainty. So a random forest, so firstly, a decision tree classifier could be classified as a tree graph of successive if-else statements, in this case pertaining to whether or not features are within a certain range, leading to a single output. While they are simple to generate and easy to interpret, a single decision tree is usually not the optimal learning model for classification tasks, especially if there is significant overlap between classes. On the other hand, a random forest classifier is effectively a collection of smaller decision trees, hence the forest, that each use a different randomly selected subset of features. With each tree producing a single output, the predicted class is the one selected by the most trees. While this generally produces better results in a single decision tree classifier, it also produces the added benefit of being able to quantify how certain the prediction is. And I'll show you in a second, I made 2 examples of the graphs. But for example, an overall prediction where all the trees predicted the same class is much more likely to be correct than a prediction with an even distribution between the classes. Therefore, if need be, we can prioritize detections that are classified at a greater level of certainty. So here's an example of a decision tree classifier. So say this feature right here is 0.016 and it's less than 0.018 as shown right here, then it goes to the left. So on and so forth, the same and the same. And this one, more killer whales ended up in this box. So this is predicted as a killer whale. This is an extremely simple decision tree. Decision trees typically are created until all the end leaf nodes have just a single class in them. But I needed to put this in a slide, so I couldn't show the entire thing. But as you can see here, there's only one output, and there isn't really a certainty metric at all here. It's just, you predicted killer whale, that's it. Whereas with a random forest, it's a bunch of decision trees that are randomly generated using random selection and a smaller number of features than the ones that you've selected. And these are, understandably going to have different results, because sometimes you'll have something, say, something that lines up with killer whale for a good, like, a fraction of the features, whereas another fraction of the features mostly lines up with humpbacks. And so right here we have an example where 7 of the 10 trees here predicted killer whale, 2 predicted humpback, and 1 predicted vessel. And since most of the trees predict a killer whale, it's predicted as a killer whale. Now, let's say all of the trees predict a killer whale. Chances are it's a killer whale. If half the trees predicted humpback and half the trees predicted killer whale, then we're not entirely so sure, are we? So effectively, what this is useful for is we can prioritize which detections we actually look at if we were to plot this onto a map, or alert people about nearby killer whales. And I'm just gonna go back. One run that I had, this wasn't done on a very good set and wasn't using the best model, but when the lead of the most predicted class is really high, you get much better results. Whereas if the lead isn't actually lead is only like 0.17, which is not very big, you get pretty crappy results. So if you have a detection or a classification that isn't very clear, whereas you have some other detections that are a lot more clear, it's better to focus on the ones that have more accuracy. Anyways, that was pretty much it. We've been running many different runs of the test classifier in Jupyter Notebook lately, and we've been getting very different results. As I mentioned before, the histogram boosting classifier, which, as I mentioned, I can't really explain very well, has been having very good results. And we've been in sort of the 85% range if we don't ignore certain detections. But if you ignore the ones that have the lowest accuracy, or the lowest certainty rate, as I mentioned before, we get into the 90 to 95% range of accuracy. So yeah, anyways, thank you very much.
Thanks, Stephen.